2024 A-Level Combined Mathematics Paper 2 Part A question number 4. This question has to do with power, i.e. the rate of work done. The question says, a car of mass m kilograms travels along a horizontal straight road with its engine working at a constant power of p watts. There is a constant resistance force of r newtons to the motion of the car. Given this, we are asked to find the acceleration of the car at the instant when its speed is equal to u meter per second. Now after this, the question then says, now the car travels at a constant speed up a straight road that is inclined in angle theta, which is in between sec and pi by 2 radians, to the horizontal. Given this new situation, we are asked to find the constant speed of the car if the car is subject to the same resistance of r newtons and has the same power of p watts. Now to start off with this question, let's go to the first part, which says that our car is moving along a flat horizontal road and it has a mass of m kilogram, a power of p watts, and goes at a speed of u with a constant resistance force of r newtons. Now drawing this on a diagram, let's assume that our car accelerates forward at an acceleration of a. And given this, let's mark out everything else. So we know the car travels at a speed of u meter per second, so we'll mark that out. We also know that there's constant resistance force of r newtons in the reverse direction to the direction of motion. Therefore, we are moving in the rightward direction, r is in the leftward direction. In addition to this, if we're accelerating the forward direction, then the engine of the car must be pulling us in that direction. So therefore, I'm going to mark a force from the engine in that direction and call it, let's say, F. In addition to this, we also have two other forces which I don't really have to mark, but I'm going to mark them anyway. We have the downward force due to gravity, which in this case, since our car weighs m kilograms, is going to be equal to mg Newton downward. And in addition to this, since our car is not falling through the floor, we must have a normal reaction to this force, which is going to be equal to also mg Newtons. But in this case, instead of marking that, since it's not actually relevant, I'm just going to call it S1. Now with this, we are done with marking all of the forces. Now what we can do is to consider F equals ma, another equation based on power, in order to find the acceleration a of this car. So first off, let's apply F equals ma to the car. Now in the vertical direction there's really nothing relevant, so all we're going to do is to apply F equals ma in the horizontal direction. So doing so, we can see in the rightward direction we have F newtons, on the leftward direction we have R newtons, so that's going to be F minus r in the rightward direction, and that's all of the forces here, which is going to be equal to m times a. In this case, the mass of the car is capital M and a is a. Acceleration is marked as a. So therefore, we get capital F minus capital R equal capital M times a. This is going to be equation number 1. Now in addition to this, we can get another equation. As we know, whenever you have a power acting to create a force, power is going to be equal to the force times velocity. Now this of course means that when you move faster, the same power will apply less force in your engine. So from this, if we take this equation, we can see, applying the variables, we have our power being equal to p, we have our force being equal to F, and we have our velocity being equal to u. Therefore, we can also get the equation p equal F times u, which could be rearranged to get F equal p over u. And this is the equation I will be using in order to substitute into here in order to find a. So I'm going to call this equation number 2. Now with 1 and 2, what I can do is to substitute 1 into 2, and if I do that, I'm going to get, instead of F, p divided by u, so I'm going to get p divided by u minus r equal capital M times a, and therefore rearranging, I get a equals, and if I divide both sides by m, I get 1 over m times p over u minus r. And here in this equation, all 4 values other than a are known. M is known since it's given in the question, p is known since it's given in the question, r is known since it's given in the question, and u is known since it's given in the question. So therefore, we have everything we need here. If I were to add anything to this proof here, the only thing I'd add is a mention of the fact that F is the driving force of the car. It's the force due to the engine on the wheels of the car. So I could mark that. I could just say something like, let F be the driving force or something, driving force. But other than that, there is nothing else to solve here in order to find the acceleration a of the car on the flat horizontal road. Now after this, considering the second situation, we have a car traveling at a constant speed up a straight road inclined at an angle theta, and it has the same power and the same resistance force. And given this, we're asked to find the constant speed. Now in this particular situation, since our car is traveling at constant speed, the acceleration upward is 0 meter per second squared. Since if it was accelerating, we would have a change in speed. So due to this, we can just not mark the acceleration and just mark the velocity. So in this case, I'm going to mark the velocity as v, and I'm also additionally going to mark everything else that I know. So I know the angle to the horizontal here is theta, I know the resistance force is r, and therefore this force is r, and I also know the downward force here is mg. In addition to that, I'm also going to mark this force here as S2 and the force due to the engine, similar to what I did over here, as F dash. And similar to what I did over here, I'm also going to write that F dash is the driving force. So I'm going to take this diagram, I'm going to make it a little bit smaller here. I'm going to take it to the side. I'm going to write let F dash be the driving force, or you could say something like driving force of the engine, but in this case I think just being the driving force is sufficient. So with this second situation, what we can do is similar to what we did in the first one, where we apply F equals ma in a given direction and then use this law to relate power, force and velocity. So in this case, I'm going to do apply F equals ma. I'm going to apply it in the direction up the slope. So I'm going to apply it in this direction. And doing so, I can see up the slope I have F dash, down the slope I have r, and also down the slope I have a component of this force mg. So I have F dash minus r and minus a component of mg. So down the slope the component, if we take a look, if this angle is theta, this angle is pi by 2 minus theta, and therefore this angle is theta, and to this angle theta here, the side we'll want is opposite, and therefore it is mg sine theta. So according to that, we have F dash minus r minus mg sine theta. Now, considering the right side here, we have m times a, and m is capital M, and a in this case is equal to 0, since we were given that our car is traveling at a constant speed. So therefore, the right hand side of our equation is m times 0, which is just 0. So we can write F dash minus r minus mg sine theta equals 0. Now in addition to this, similar to what we did in the first part of the question, I can apply power equal force times velocity and say that in this case the power is P, so we have P equals, and for force I have F dash, and for velocity I have the velocity V that I marked over here. So therefore I have F dash times V. Now what we're going to do here is to divide both sides by V and substitute instead of F dash P over V. So from this I can get F dash equals P over V, and taking this into here I can get P over V equals, and taking the other stuff to the other side I have R plus mg sine theta. Now since I want V, what I can do is to swap this thing and this thing, take V up, take R plus mg sine theta down, and if I do that I can see I get V equals P on top divide by the whole thing of r plus mg sine theta. Therefore I get V equals P divided by R plus mg sine theta, and that is my final answer for the second part of the question. Now with that, let's go ahead and discuss the marks award for this question. So at the start, when you draw this diagram here, you actually don't get any marks. Instead, you get marks for finding the equations relevant to this diagram. So going down, for applying F equals ma and writing down this equation right here, you get 5 marks. After that, for applying power equals force times velocity and getting P equals Fu and dividing both sides by U to get F equals P over U, you get another 5 marks. After that, when you combine the two and get the equation A equals 1 over M times P over U minus R, you get another 5 marks. Moving on from that, for the second part of the question, again, for the diagram you actually don't get any marks, but when you apply the equations, for applying F equals ma in the relevant direction and getting this equation right here with the sine theta and everything correct, you get 5 marks. And then when you apply the power equation, get this thing, substitute, simplify and rearrange to get V equal P over R plus mg sine theta, you get a final 5 marks. And with that, we are done with this question. So I hope you enjoyed. If you have any feedback, post them in the comments down below. If you have any questions, post them in the comments down below. Thank you for watching, and goodbye.